In this video, we are going to introduce you Super Terahertz Image Enhancer. You click on the executable icon and the software runs. Now you indicate the folder that you've saved the raw terahertz data. You open it, and in the meanwhile, please make sure that the numerical aperture of your system is entered here correctly. For my system, it is 0.35. The pixel size, which is the stepper motors steps of your raster scanning system, should be entered here. For my case, it's 50 micrometer. The thickness of your object is gonna be entered in this panel. For my case, I am using a packaged integrated circuit as my imaging object, which thickness is 2.3. The K factor of my imaging system is 1, and the sampling rate, which is 1 divided by the steps of the signal in time domain, is 10.9. In other words, sampling rate is the data acquisition rate of the system. Once the data is loaded in the system, you can see the terahertz raw terahertz image, which is here. If I full screen on it, I'm gonna select the edge of the sample, say 14 by 72. I'm gonna put 50, and I update this panel. And now I have both of the beams, reference beam as my mouse is showing, and the sample beam. What I need to do in this step is finding the time intervals of the sample beam, which is 2.5 and 255. I enter them here, 2.205, I'm sorry, and I'm gonna put it 250. I update. I'll see that the image, the terrace image of the sample is being developed here, which is the maximum minus minimum of this sample beam. And then the software also analyzes the time domain version of the signal, and due to the fact that the diffracted beams diverge and have more time delay, it can filter out the diffracted beams and suppress the blurring effect of diffraction on the image. Then I'm gonna push this button and compute the spectrum, and as you see here, and also the absorption graph and point spread function. What you need to be careful about is this parameter defocus, because we are imaging a packaged item, and we don't know exactly if the layer that we are imaging inside that item is located on the focal plane or not. The software finds the defocus, which means that how far the object is located on the z-axis from the focal plane. So I'm gonna start from 0, meaning that we assume the layer that we are imaging is exactly on the focal plane. We get this point spread function and this image. So I'm gonna increase it to 0.1. Not much of difference. I'm gonna increase it to 0.3 millimeter. And as you see, as we are going farther from the focal plane, the point spread function gets bigger. And I think that the image gets blurrier, so probably we should not go farther. But just to show you how it works, I'm gonna go to 0.5. As you see, it computes the a point spread function at 0.5 from focal plane and computes the convolution of the point spread function and Terahertz image and gets this image. So I'm gonna go back to point 1, and as you see we have the best image here. So I had done a good job on aligning my system and putting my sample on the focal plane. Maybe even it's exactly on focal plane. Let's see. Yes. So in the next step, you take a look at um, the spectrum of your sample, and you you find out up to what point you have some imaging signal. It appears to me that 2 terahertz is the highest frequency that we have some signal before it becomes totally noise floor. So for my frequency domain filter, I enter the high frequency cutoff of 2 terahertz, and I also enter the low cutoff frequency of 1.5. The reason that we use a bandpass filter is the fact that first we would like to filter out the low frequency part of the spectrum, which causes more diffraction, and then we filter out the high frequency part of the spectrum, which causes the distortion, noise distortion on the image. And you push this button to compute the frequency domain filtering, and after a few seconds you will get the image in this panel, as you see. And in the next step, you push this button to compute the convolution. As you see, the software models the point spread function of the frequency filtered beam and compute the convolution of this point spread function and the image. And we get a very high resolution version of the image. If you would like to measure the size of the features on this image, you can click on full screen and you can see the size of the features. You can also save the file as as JPEG, BMP, TIFF, or any type of image that you would like. One other thing that I would like to show you is the X-ray image of the sample, which is here, the optical image of the sample, and the steps that we did to develop this high-resolution Terahertz image. As you see, the size and the shape of the features in this high-resolution Terahertz image that we got can be confirmed by the X-ray image. So if you are in the industry that you would rather to use non-ionizing beams to develop a transmission image of your packaged items, or you don't want to spend a lot of money on an X-ray system and you would like to have a portable system, you can use Terahertz image along with this resolution enhancement software to develop high resolution image of your packaged items. Please feel free to reach me out if you have any questions, and I would be happy to answer. Thank you very much.